Okay, guys, this is section 3.3, part 3. The first part of section 3.3, we just talked about what a logarithm is, what a log is, logarithm. The part 2, we used logarithms to solve equations. And now part 3, we're actually going to look at equations that have logs in them. Okay, there's 2 times where there's equations that we're going to at least talk about that has logs in them. So the first thing we're going to talk about is earthquakes, and the next thing we're going to talk about is sound. Those are 2 places where there's logs right in the equation. Okay, the relative intensity, all right, of an earthquake is measured, is a measurement of ground movement. Okay, so the relative intensity is kind of like the raw data. The relative intensity of an earthquake is a measurement of ground movement. Then what we do, though, is we change this into a magnitude. We take this information and change it into a magnitude. We've all heard that, right? The magnitude of different earthquakes. All right, the magnitude of an earthquake correlates to the Richter scale that relates this relative intensity using, guess what, guys? Using logarithms. All right, or better known as, we just call it logs. Okay. So the magnitude of an earthquake, which correlates to stuff on the Richter scale, actually relates to this relative intensity, this raw data that they're getting about how the ground is moving. And they change that. The magnitude takes that relative intensity and does something with logarithms. All right, and it's pretty easy. Magnitude is equal to the log of the relative intensity. That's it. The magnitude is equal to the log of the relative intensity. Now, why on earth would we do that? Well, here's the problem. Down here, this line, see how it kind of looks thick? There is a ton of earthquake measurements down here. There's a ton of earthquake relative intensities that are very, very small. But then you also have huge earthquakes every once in a while, all right? And we don't want to disregard those because those are the most important ones, right? Those are the ones that we feel and we have issues with. So this is an issue. I can't just have a line here. I have no comprehension how many earthquakes there are or what's going on. There's a whole bunch of small ones here. But the relative intensity, the problem is the relative intensity can vary greatly. Look, this is all kind of by zero. This is even in the millions. So this up here is like 125 million. Okay. When we take the log of these, look how they spread out. See the difference? You can now start to see a whole bunch of things. Let me show you one thing. If you take, and I'll write this down too, let's clear it. If you take the log of 8, okay, the log of 8, and this is just, you can watch if you want, the log of 8 is equal to 0.9. Okay, so that's still a number. I mean, it's almost 1. That's we can deal with. And let's just, I mean, these are in the millions. Okay, let's do log of 8 million. Right, that would be a million. All right, so let's do log of 8 million. 1, 2, 3, 4, 5, 6. That equals 7. So now we're talking about something as small as a relative intensity of 8 versus a relative intensity, this actually was technically 6.9, but I rounded it to 7. This is point. A log of 8 million, this we can compare, right? We could still plot something like almost 1 and something like 7. Those are doable. So taking a log causes a number to grow very, very slowly. Compared to 8 versus 8 million, it's a lot easier to compare 1 versus 7. And that's what's happening here. All these that are too hard to see, all of a sudden become at least visible. Okay, there's still a lot going on, but you can at least see them. It breaks it apart. Let's try this one. This one here is, we said, what do we say, like 125 million. So let's do log of 125 million. Okay, so 120, oops, let's do log of 125. And that puts us at right around 8, which is this guy right here. Okay, we could do one more. This one lands so closely. This is what, 40 million? So let's do log of 40 million. Okay, log of 40 million, so log of 40 million. And that is, oh, let me write this down. This is what? This was basically 8, which is that guy. Let me even get another marker here. This turned out to be something like 7.6. And that is, so this guy here in red is this guy right here. Okay. Notice those are my top 2. Those are my top 2. We probably could find this guy and this guy, but you can see how I just changed this 125 million into 8, which now I can correlate it to all the rest. Okay. So that was his idea. That was Richter's idea of correlating relative intensity to a magnitude, which a magnitude is much easier to compare. All right. Let's take a look. Another place, and then we'll go to some examples. The other place that we can see logs is sound. They use that for decibels. We've all heard decibels. That's how we measure sound. Same thing. Relative intensity is actually the measurement of the sound. We take the log of that. They just did something a little bit different. They took it times 10. Okay, and that creates the decibel. Okay, so let's try some examples. So some of the examples will be earthquakes, and then some of the examples will be sound. Those two things, and then we're good. If the relative intensity of an earthquake is 6,840, find the magnitude. Okay, so you just have to look it up. I'll give it to you on the test. Magnitude is equal to the log of the relative intensity. Okay, I can write that up, where you can just flip back to your first page. I'll abbreviate it like this. So we can put it here for a second. Magnitude, so I'll just do M, is equal to the log of the relative intensity. Okay, it's just a conversion so that we can kind of convert this raw data, this relative intensity, into a magnitude, which is easier to compare all earthquakes. All right, so we know relative intensity, 6,000, so magnitude, and it says find the magnitude, so that makes sense. That's my M. Log of 6,840. All right, and then you simply type that in. Notice it's base 10, so you can use your calculator. That's really nice. So you're just going to do log of 6,840. And then it'll tell you how many places to run to. This will go out 3, but usually it's 2. Oh, we can go out 2. It's 3.835. So the 5 would make the 3 go up to a 4. Okay, good. All right, how about, can we do the reverse? Let's see, if the magnitude is 2.8, can you find the relative intensity? Okay, so same equation, magnitude equals the log of the relative intensity. Okay, so here the magnitude, 2.8, can you find, I'll just do R for relative intensity. Okay, can you find the relative intensity? Now, this looks crazy, but I'm just going to reverse it. I'm going to write it as log R equals 2.8. Okay, so I just flipped it over, and now it makes so much more sense to me. Now I'm going to swing it around. What's my base here if nothing's written? Base is 10. 10 to the 2.8 power equals R. Bring it around. Write it as an exponent. 10 to the 2.8 equals R. And then let's do 10 to the 2.8. 10 to the caret 2.8 gives us 630.957 equals R. What does that round to? This to 2 places, this would bump it up to 96, right? But if it says something about to the nearest whole number, this would actually go to 631. I've rounded to 1 decimal point. Okay, so that 5 is making that 9 go up, which takes us then to 631. So even to 1 decimal place, it's still 631. Okay. Good. Okay, this one's just a little bit harder. In 1994, an earthquake measuring 6.7 on the Richter scale, so remember the Richter scale is magnitude, okay, occurred in Norridge, California. In 1958, an earthquake measuring 8.7 occurred in the Kuril Islands. How many times as tense as the Norridge quake was the Kuril quake? Okay, so when we want to compare, we have to compare with the relative intensity. We have to use the raw data. So we might need a little extra room here. Okay, so for Norridge, California, so in California, okay, we want to do magnitude equals log of relative intensity. Okay, we have the magnitude, but if we want to compare these two, how many times as intense, then we have to compare that with the relative intensity. So we're going to put in a 6.7, okay, and then I'm just going to do R instead of RI, and now I have to solve that for R. So I'm just going to take the time to rewrite it, and then swing it around, okay. So 10 to the 6.7 equals R. Okay, we don't even have to type this into our calculator, okay? Now, let's try the Kuril Islands. All right, so same thing. So magnitude equals log of the relative intensity. I'll just do R for relative intensity. All right, its magnitude was 8.7. Okay, so 8.7 equals log of R. Rewrite it, log of R equals 8.7. Okay, and how do I solve for R? Bring it around. Write it as an exponent. 10 to the 8.7 equals R. Okay. And you don't even have to figure that out. So for this problem, make sure when you come to it, I just need a little extra room here, so we're going to slide this up. Okay, we'll be okay. Somehow they've got extra room up at top, so we'll have to change that. Okay, so it wants to know how many times intense as the California was the Kuril, okay? How many times do I have to multiply this to get to this guy? Is it 2 times as intense? Is this guy, if I take this times 2, will I get 8.7? Is it 3 times as intense? Do I take it times 3 and then I get it? What do I have to multiply this guy by? That would be how many times to get this answer? That's what they're asking. How many times as intense was the Norridge quake, or as the Norridge quake was the Kuril quake? Okay, they want to know, what do I have to multiply this by to get this guy? Okay, that's what this question is asking. So look for it on the homework. Okay, I just want to know what I have to multiply it by. That'll tell me how many times. Is it 4 times? Is it 7 times? Okay, now look at this problem. You're multiplying, right? So all you have to do is divide. Divide. Okay. We have to compare relative intensities. That's what we're doing here. Let me slide up even a little bit more. Okay, we're comparing relative intensities. This was the relative intensity of California. This was the relative intensity of the Kuril Islands. Now, what do we do when our bases are the same and we're dividing? Does anyone know what do we do when the bases are the same and we're dividing? Our answer is 10. And then we subtract the exponents. 8.7 minus 6.7. You want to subtract these exponents. And that answer goes on 10. These numbers have to be the same, which they are. Then you subtract the exponents. Okay, when you're multiplying, think about this, guys. When you're multiplying, you add exponents. When you're dividing, you subtract exponents. And so x equals 100 squared. Okay, so what was x? So 10, can we still see it? Yeah, 10 squared is 100. So x was times, so it's 100 times. I had to take this times 100. That's how many more times this corral quake was. That's how much bigger it was. 100 times bigger than this guy. 100 times bigger. Okay. All right, that one's a little bit harder. Try it. You have to compare the relative intensity. So the first thing I did on that was I found relative intensities. Okay, so now these last three deal with sound. So let me see if I have it. Don't forget the sound one. Decibels equals 10 times the log of relative intensity. Okay, so I'll do decibels equals 10 log, and I'll just do R for relative intensity. Okay. All right. If an adjustment raises the sound on your radio by 4 decibels, how is the relative intensity of the sound affected? Okay, so basically we want to know 4 decibels. This is a fancy way of saying, okay, 4 decibels is what relative intensity? That's what they're trying to get us here. So we want decibels equals 10 log of relative intensity. Okay. How is this how is the relative intensity of the sound affected? So we're trying to figure out what's happening here with the R. We know the decibels is 4. Can we come up with what's happening with the relative intensity? 4 decibels, this is just another way of saying 4 decibels is what type of relative intensity. So this is regular old multiplication, so we're going to divide by 4, or divide by 10, right? 0.4 divided by 10, or not, what am I saying? 4 divided by 10, okay? You could leave it like, you can leave it as, and we did this earlier, right? You can do this as 4/10, you can do it as 2/5, or you can change it to 0.4. Okay, I'll change it to 0.4. I kind of like that. Okay, it's worth it. I think this looks crazy, but as soon as I take the time to write the log on the left side, I just literally flip it over. All of a sudden, now I see my pattern. I'm so used to doing specifically this that even I still write the log on the left side. Okay, so now 10 to the 0.4. 10, remember if there's no base, it's a 10. 10 to the 0.4 equals R. Okay, and so this will tell me about the relative intensity. 10 to the 0.4, let's type that into our calculator, 10 caret 0.4 is right around 2.5. Okay. So 2.5 is our relative intensity, okay? Or I think in this case it's 2.5 times. Okay. All right. Suppose we have a stereo speaker playing music at, let me make sure you guys can see this. Okay. Suppose you have a stereo speaker playing music at 60 decibels. What decibel reading would be expected if we add a second speaker? Okay. Now, if we add a second speaker, something has to double. But it is not the decibels. It is not the decibels. What would double? You're exactly right. What would double, though, if we add another speaker? The relative intensity. The relative intensity has to double. So we kind of have to do this problem twice. What we have to start out is we have to change this decibels to relative intensity, because that's what doubles. So I need decibels equals 10 log relative intensity. Okay, so 60 decibels. I need to find the relative intensity so that I can double it. Okay, so I'm going to divide both sides by 10. And I get 6 is equal to log of R. Take the time to rewrite it. Log of R equals 6. Bring it around. Okay, bring it around. So one speaker has a relative intensity. Well, let's just bring it around. 10 to the 6 equals R. 10 to the 6th equals R. Okay, bring it around. 10, remember if there's nothing there, it's a 10. 10 to the 6 equals R. That is one speaker. One speaker is 10 to the 6th. Now, two speakers, okay, two speakers, now it's okay to double the relative intensity. So two speakers is 2 times 10 to the 6th. Okay, it's okay to double the relative intensity. So I had to change decibels to relative intensity. Okay, and I'm just going to leave it like this. This is actually easier to work with. So this is one speaker. Now it's okay to double the relative intensity. Okay, but now what does the question say? What decibel reading would we get if we added a second speaker? So now this is a relative intensity with the two speakers. Now I want to change it back to decibels. Okay, so now decibels equals 10 log of my relative intensity. Well, now two speakers, I went ahead and doubled. So two speakers, this is now the relative intensity. So decibels equals 10 log, and then just take your time, type all this in. 2 times 10 to the 6th. Okay, if you want to get that number, that's okay. Otherwise, just take your time with parentheses depending on the type of calculator you have. If you change this to a decimal, that's all right. Just take it out maybe 4 or 5 places because it will affect the answer. So take this out as far as you can if you have to do that. It should be pretty close to 63. Okay, and that is your decibels. Decibels is dB. Okay, so we doubled the relative intensity. But notice it doesn't even come close to doubling the decibels. Okay, but that's okay. That's because the log shrinks all those values down. Okay, so we doubled two speakers. Where was it? If you added a second speaker, so two speakers doubles the relative intensity, but does not double the decibels. All right, let's try this last one. The loudness of a sound, now see if this makes sense. The loudness of a sound decreases as the distance from the source increases. So as you walk away, your distance is actually increasing, but what's happening in the sound? You know, the further you get away from something, the sound decreases, okay? Tripling the distance from a sound source, such as a jet engine taking off, multiplies the relative intensity of the sound by 1/9. Okay, so here, instead of doubling it, taking it times 2, because we're walking away, it should go down. So we're actually going to multiply it by 1/9. Okay, but that's because we're walking away, the sound gets less. Okay, here we added another speaker, the sound gets more. Okay, if the sound from a jet engine taking off has a reading of 140 decibels at a distance of 50 feet, what is a decibel reading at a distance of 150 feet? Okay, so tripling the distance, okay, and that's what they specifically asked us for. They tripled the distance, okay. What happens to the relative intensity? Okay, it goes down by 1/9. It goes down by 1/9. Okay, all right, so let's start out. It asks for the decibel reading, so we have to do the exact same thing here. Decibels equals 10 log of relative intensity. Okay, we have the decibels. We're talking about 140 decibels. Okay. All right. Oh, what am I doing? This is R. That is not 4. Okay. So we are going to divide both sides by 10. Takes us down to 14 log of R. I'm going to rewrite it, make sure you guys can see. Okay. Log of R equals 14. So I just flipped it over. 10 to the 14th equals R. 10 to the 14th equals R. Okay. Now, what happens to the relative intensity? It goes down by 1/9. It goes down by 1/9. So this is the relative intensity at 50 feet. Okay, so 50 feet, the relative intensity is 10 to the 1/4. How am I going to figure out the relative intensity at 150 feet? Well, I simply have to, instead of taking it times 2 like I did up here, I take it times 1/9. It's 1/9 of, what does of mean in math? Of means time. So it's 1/9 of my 50 feet. It's 1/9 of my 50 feet. Okay, and then that is my answer, except that's the relative intensity, and I want decibels. So now I do decibels equals 10 log, and we could just write this a little bit different. We could write this as 10 to the 14th divided by 9. We want to take 10 to the 14th divided by 9. We want to take the log of that, and then take it times 10. Okay, so I could do it like that too. Like if you have a scientific calculator, let's clear this out. You might have to do 10 to the 14th and then divide that by 9 and then take the log of that answer. Oops, that's not what I wanted. I want the log of that answer and then take it times 10. Okay, and that should be 130 if we round to 0.5. Okay, this went into some scientific notation. So try really hard to just keep going. Try not to have to write this down, even if you had to do it in pieces. Did you see how I took it times 10 to the 14th, took it times, or divided it by 9, and then just went ahead and took the log of that answer. If your calculator can handle the whole thing, then just type the whole thing in. Okay, should we see that? 10 log, and then it's 10 to the 14th, bring it down, divided by 9. Okay, gives us the same answer. I don't know if you guys can see this one as good, but so yeah, just take your time. But for these here, if you're going to do comparing, you have to compare relative intensity. So we had to change the decibel to relative intensity, double it or take it 1/9 of it, and then change it back to decibels. All right, give it a try.